Okay, welcome everyone to this week's webinar sponsored by the Chicago DOE Alliance Center. Today we turn our attention to some high pressure earth science problems. I'm pleased to introduce Wang from the Department of Earth and Planetary Sciences at Northwestern University. Fei is a PhD student working with Steve Jacobson, one of our CDAC partners, and will be defending his thesis, I understand, in 2 weeks. And despite this being a very busy time, he's graciously agreed to give a talk in our webinar series. Fei has a bachelor's degree from Nanjing and a master's from Peking University, and has been at Northwestern since 2015. And throughout this time, Fei has been quite productive. According to his CV, he has some 15 publications and a number in preparation and 2 patents. So we're very much looking forward to your talk. Thank you.
Thanks, Raj. Thank you for the introductions and also the invitations. It's an honor to speak here at CDAC. So I would like to start my presentation with this title, the high pressure crystal structure and ordering of hydrogen-related defects with ferriiron silicates of the metal transition zone. So from the title, you probably already know that I'm more interested in, I'm a geologist, so I'm very interested in metal transition zone, which I'll explain later what that is. And so because I'm interested in Earth materials, so that's why the reason why I'm interested in high pressure research, because those research could generate high pressure and to simulate environments similar to the Earth material. So in that case, we'll be able to see how the metal minerals, the physical properties of metal minerals change with pressures, and that will help us to explain the observation from other geophysics fields, such as seismology. So in my presentation here, for my presentation here, is basically for 3 parts. So first one, I will give a short introductions about Earth, the Earth mantle. And then the second part is actually also divided to 2 parts. It's the high pressure experiments I did here at Northwestern. So first one is the Wazlight, and second one is Japanite. And last, I would like to talk about a program I wrote. It's called HiMath. So it's a Python-based program, so we can see how we use the data collected in high pressure research and connect those information with other geophysical observation. In this case, it's seismology. So to start is, well, I would like to start with the Mother Earth. So here's a picture of Earth. We're all very familiar with that. So probably most of you are also familiar that Earth is not a homogeneous sphere. So generally, Earth can divide it into 4 parts. It can have an inner core, it can have an outer core, it can have a mantle, and then lastly, it's a crust. So each layers has completely different composition. For example, outer core is basically liquid irons with some light elements, and the mantle is basically silicates minerals. But this is only a very simple way to divide Earth into different layers. So for the mantle itself, you can also divide it into 2 parts, upper mantle and the lower mantle. This is much easier to see in the cross sections I'm showing you here. So the upper mantle and lower mantle has very similar compositions, but the phase is very different. So transition zone, which I highlight here as the blue circle, this one, is 10 layers located at depth 410 to depth 660s. So it serves as a transition place for the upper mantle phase transform to a lower mantle phase. So that's how it gets its name, transition zone. So what's interesting, why I'm interested in transition zone, what's interesting about it is that to answer that questions, you have to look a little bit into the detail of what transition zone, the phase of transition looks like. So here I'm showing you is the phase diagram of the upper mantle, transition zone, and lower upper mantle. So from here, you can see that for the transition zone, the phase is basically beta spinel, alpha spinel, and meteorite garnet. So its names beta spinel and garnet spinel is because this is the phase that directly transformed from the previous phase olivines. That's the alpha one. The beta spinel also has another name. It's called Wazlight, and and the gamma one is called ringwoodite. And here I also show is the composition of it is MgFe2SiO4. So you might feel that there's nothing strange, especially the title of me actually say about hydrogens. That is because that for wasserite, remoudite, as well as olivine and garnet, they also have another name. It's called nominally anhydrous minerals. So that is nominally is anhydrous, but actually in the real world, because there's no perfect crystal, there's a crystal defect in it. So hydrogen can actually replace a magnesium or silicates and into the crystal structures. So that's how its names come from. And the second one you might think is that, well, so what was strange, because previous study also showed that for wasserite remoudite, the maximum water solubility is only like 3 weight percent. It's only 3 weight percent is not much. Consider this is the Earth we know. So it's covered with ocean. 70% of the surface is covered by water. And I also recently just found a figure from USGS. Last week is actually World Water Day. So they actually show how much water on the surface. So this tiny little blue box here, blue sphere here, is the water in the lake and river. And the middle one is actually the fresh water on the world. And the last large one is actually the oceans, and all the waters combined on the surface. So this is the water we see on Earth. You might think that this is quite enough, but because the transition zone, although in the previous slide it looks like just a tiny little layers, it actually is still much larger than the crust we live on. So even though only 0.2 weight percent of water on average in the wasserite remoudite, if I extract all the water from it, it can mean there's another water sphere hidden in the Earth. That's the hidden ocean theory. Right. So this is the theory we have. So the next question is, do we have a direct evidence? And the answer is yes. So in about 10 years ago, slightly less than 10 years ago, so people, Pearsons found remoudites as a diamond inclusion from Brazil areas. So this is the diamond they found. And here, the tiny spot is the remoudite they found. And they actually took the infrared spectrums, and they were able to see that it contained about 1.4 weight percent of water. So this is the first direct evidence that actually indicate that in Earth mantle, at least mantle transition zone, at least at regional scale, it could be hydrous. So the real question is, this is the only evidence we have, and we do DAC experiments, so we know how expensive diamond is and how rare diamond is. So is there any way for us to evaluate how much water in the mantle, especially transition zone? And the answer is yes, because when a large earthquake happens, it usually generates a seismic wave, and from the all over the world station, they will record the arrival time, and they will be able to see the seismic wave. So because of this, we actually can inverse from the observation to see the seismic wave travel in the Earth interior. And so if you know the minerals in the Earth, and if we'll be able to see the elastic properties and density, we'll be able to play with the data to constrain how much minerals, all the specific components in the minerals in the Earth interior. So that's the theory, and that's basically the general stories of what I did in the past few years to collect data at high pressures and use those data to explain seismology observations. So I'm going to start with the first experiments, the wasserite. So probably I don't need to mention how important wasserite is, because it's contained like 60% of volume in the mantle transition zone. That itself already stated how important this mineral is. And here I'm showing you is the crystal synthesized from high pressure experiments. It looks really pretty. But if we will look a little bit detail into it, to the atom scales and see the unit cell, this is what the cell looks like. And it's quite normal. And if it's anhydrous, I mean, the ideal case is orthorhombic symmetries, which means that probably has a mirror symmetry elements in the crystal structures. So nothing very special here. Here's the interesting point. So if we actually zoom in into part of it, we can actually see about that's two M3 sites. So here I'm labeled M3A, M3B. So M3A is behind the mirror, the blue wall. So if it's anhydrous, without hydrogens, without crystal defect, M3A and M3B will be identical. That's why there's a mirror there. But previous study also showed that hydrogens, when replace magnesiums into the wasp structures, it's not just randomly replace one, they prefer one side and another one. So because of that, M3B side and M3A side actually split because it's not the same, not identical. And that caused the mirror symmetry break. And also the crystal symmetry change from orthorhombic to monoclinic. Previous study have already shown that because of water, this could happen. But the real question is what happened at high pressures? So is that remain orthorhombic symmetries, or because of the hydrogens, you can actually break the orthorhombic symmetry and become monoclinic symmetry at high pressure? So this is the one study that not been able to identify yet. So that's what one thing I'm interested in. And also, because waslight can contain hydrogens, it also means they can have hydrogens bond here. So in here, actually I'm showing you is the hydrogen bonds. So if you look into a little bit detail about these hydrogens, show you here. So here's actually the general position, general pictures of the hydrogen bond. So the red dot here is represent the oxygen atoms, and so we have two oxygen atoms, and the white one is represent the hydrogens. So excuse me. So in normal normal times, the hydrogens were close to one of the oxygens, and then because of the energies curves. So what I'm showing you here, the red curves actually represent how the energy looks like if there's two oxygen atoms there and one hydrogen atoms there. So the interesting point is that if we give a pressure here, so we compress the oxygens, and then the oxygen distance will get closer. And because of that, the energy curve will not remain the same. It will slightly change. So if something looks like this, so now from the previous slide, I have two minimums, and the hydrogens clearly prefer one of the energy minimums. Now, because the energy curve compressed, the two minimums getting closer, and the energy level is getting closer. So the two minimums is going to change it to one. So in that case, the hydrogens might possibly move in the middles. This is the phenomenon that usually have been observed in other minerals, or also more importantly in ice. So here's one of the interesting questions is no observation have been observed this phenomenon on waslight. So one of my interests to see that how this will happen in waslight. So that's the reason why I perform high pressure single crystal diffraction, X-ray diffraction experiments on waslight. So we have two waslight samples. One is less hydrous, contain like 0.2 weight% of water, and another one is like 2 weight% of water. So we perform these experiments at Argonne National Lab. So this is the station 13 BMC. So I work with Dongzhou Zhang. This is his stations. So I'm showing you how you can have this idea how the X-ray diffractions experiment was doing there. So I perform high pressure X-ray diffraction experiment there. So here I'm showing you is the result from the experiments. So the first thing to answer the first questions is the symmetry change. We look at the monoclinic angle. So for the two waslight samples, both samples show a change to monoclinic symmetries after 10 GPa. But here's something counterintuitive is that usually people will believe that the hydrous one will change more than the less hydrous one. But what the observation we got here is the opposite. The less hydrous one actually changed monoclinic symmetry more than hydrous. The blue line indicate the hydrous waslight and only changed to 0.1 degree. But the less hydrous one is actually changed to 0.5 degrees. So this is something very interesting. And what interesting more is that how this is going to change the equilibrium state we obtain from the waslight. So to answer that, we fit the equilibrium state using two different symmetry. So on the left-hand side, I'm showing you the hydrous waslight. So because the monoclinic angle doesn't deviate much from orthorhombic symmetries, so you can see the two lines almost overlap each other, indicate there's not much change. But for the less hydrous ones, although the deviation only like 0.5 degree, you can see that the two lines is clearly separate from each other and indicate that the equilibrium state is different. So what we got from this information is that you can see the bird modulus will remain the same, but it will inflate the first pressure derivative, and you will, if you assume the wrong symmetries, that is, if you assume the alpha symmetries remain the same, the K prime will probably be much higher than the one it really is. So this is very interesting findings. Also, I'm very interested in the hydrogen bonds. So especially to see if the hydrogen bond can change compressibilities of Waslite. So to answer that questions, we will need to see a little bit detail about the crystal structures. One interesting point is that although hydrogens could enter Waslite, it's usually contain around one special oxygens, the O1 oxygens, because this is the oxygens that's less bonded. It's only contained to 5 magnesiums, so it's likely have charge between charge values can contain water in it. And people have identified O1 is the oxygens that can connect with hydrogens. So, and also people be able to realize that the O1OA, the O104, the short one, is the most most possible O distance that contain the hydrogens. And the second one is the O103 distance that can contain the hydrogens. So now we have 2 Waslite samples, a less hydrous Waslite and a more hydrous Waslite. That will be the first control group. And also the interesting point is that because some O distance can contain hydrogens and some of the O distance cannot contain hydrogens, so we actually have another control groups. So let's see the first one. For the O distance that believed to contain hydrogens, what the difference looks like. So here the control group is the less hydrous one and the more hydrous one. So here I'm showing you, here is the blue dots indicates the data from the hydrous Waslite, and the brown and orange one is from the less hydrous Waslite. So we can so here I need to mention the why for the less hydrous one we have 2 O distance instead of 1 is that because the less hydrous Waslite actually showed the break of off-rampant symmetries. It changed off-rampant symmetry. So as the previous slides explained, O4 oxygen actually split to O4A side and O4B side. So that's why for the less hydrous Waslite, you have 2 O1, O4 distance, but for the hydrous one, it's only 1. So the interesting point I'm showing you here is that the O1, O4 in the hydrous one show a trend to stop decreasing after 25 GPa. And this trend will also see in the O1, O3 distance. This shows trend to stop decreasing, but those information was not observed in the less hydrous Waslite. So this is the first hint that because of the hydrogen bonds, those O distances could stop decreasing. So now this is the first control group. If you're going back to the other one, we can see we have a second group to help us identify this. Because from some O distance, it can contain hydrogens, but some O distance it cannot contain hydrogens. So we have a second control group. So in order to see this, we're showing you here is that the O1OA short side, O104 short side on the left-hand side, and the O101 side on the right-hand side. So O101 is believed that it's not possible to contain hydrogens, and it's true for both samples. The O distance decreased till 25 GPa's, and there's no trends of showing the hydrogen bond strengthenings. But this one's already shown you already can see that there's the hydrogen bond strengthening. So the argument based on here is that the hydrogen bond is probably getting stronger, and in that case, that's the reason why it can stop the O distance from decreasing. And because of this, it's likely that the hydrogen bonds will prefer have some isotopic effects, and so this hydrogen bond will be depleted in deuteriums. So it's likely that if in the future we'll be able to find Waslite, it will be very depleted in deuteriums. So this is something we can also apply to geochemistry. So this is a study about the Waslite I did. So the next one I want to show is about the Japanite. So you might feel that Japanite is something like you've never heard before, and that's probably the case because in the previous introduction, I've been showing that in transition zone, it's mostly Waslite, Remuna, and majority garnet. I didn't mention anything about Japanite, but this is the interesting part of it because that one way we can actually get the minerals from the interior is from diamond inclusions. One example is the previous one to show you the hydrous ringwoodite. So, but as mentioned before, the diamond is rare, especially super deep diamonds originating from the depth below for 10 kilometers. It's also rare. Right, but still, this can provide useful information to help us identify minerals in the interior. And so what the diamond inclusion found is that Japanite, these minerals can usually replace majority garnet. And that is that based on the phase diagram from the previous slides, people will expect to find majority garnet, but instead of majority garnet, they found Japanite. So the raise an interesting question is that could Japanite be one of the stable phase in the base of the transition zones? So that's why I'm interested in Japanite. And also, this is a quite lucky one because the Japanite, although people have found this for 20 years, no experiment has successfully synthesized these samples. So just like a few years ago, Joe Smith synthesized the first Japanite in the accidents run. He was trying to synthesize iron-rich rhodolite, but instead of that, he found Japanite. So as usual, I'm showing you how Japanite looks like. This is the natural Japanite from the diamond inclusions. And here's the crystal structures and crystal structures. So one interesting point is actually the O1 site. This is the cap tetrahedrals. So it's more like zircons. You have like 4 oxygens very close to M1 site and 4 oxygens far away, but still connect to the M1 site. So this is what the crystal structure looks like. So now, this is the minerals that first been synthesized, so there's so much study for it. So one thing I'm interested in is the equilibrium state, because if Japanite could replace majority garnet in earth materials, and if we would be able to find the physical property of Japanite, we were able to see if seismologists could detect this phase at the base of the band transition zone. So that's why I'm interested in doing the equilibrium state experiments. Also, the second one is Japanites can serve as the diamond inclusions, has been found many times in the diamond inclusions. So if you know the equilibrium states, we could use that data to calculate the entrapted pressure and thus prove the diamond is actually from super deep earth. So that's why I'm interested in doing the high pressure experiments. And here's, I'm showing you the results. So just simply doing the single crystal structures. And here I'm showing you is the equilibrium state and also at the active plot. The conclusion here is that the density is very similar to the garnet, and the Bird modulus, the equilibrium state, is also very similar to the similar composition of garnet. So the conclusion here is that even this phase could replace majority garnet if the base of the transition zones is almost impossible for seismologists to detect this one. And also we have, so the structure seems that the polyhedra is not changing much. So it's likely this phase could be stable till 29 GPa. But I have to emphasize here, so this experiments do at room pressures. So we're not sure how temperature can play a role in the stabilities of Japanite. And this is the iron-rich Japanite. So we're also interested to see how the iron doesn't show the high spin to low spin transitions. So we also perform a synchrotron multiple spectrums, which show on the left. So the left-hand side is the time domain spectrums. On the right-hand side is what we convert to energy domain. So before 21 GPa, the spectrum looked quite similar to each other's. But after 21 GPa, you show the change. So to better see how those changes, we also fit with the spectrums and get the SMO shifts and quartal splittings. So here is what it looks like. And we can see after the 21 GPa, the azimuth shift and quartal splitting significantly change. So based on those informations, we suggest that Japanite can actually suffer a spin transition from high spin to low spin transitions, and it's most likely happen on the M1 side, because if you remember from the crystal structures, it's zircon-like. They have like 4 oxygens close to each other and 4 slightly away from it. So it's likely they can collapse due to the spin transitions. So here is the study about the Japanite. And then, so you might be curious that, okay, you have seen I did high pressure experiments, we get some data, but how those data could be linked to the real earth science problem. So that's why I wrote a program. It's called HiMath. So what I'm showing you here is what the program looks like, the GUI. This program can use a thermodynamic database collected from previous studies, because for almost decades, people have did high pressure experiments on the mantle minerals. So we have very good thermodynamic elastic parameters. And based on those informations and the idea about the pressure and temperature in the Earth, we will be able to calculate the phase diagram. So this diagram is very similar to the one I showed you in previous slides, because they calculate basically based on the same way, use the same composition, same temperature profile, and also assume the same minerals stable. So we have the phase in Earth as a function of step, and we have all the thermodynamic properties. We were able to calculate the predict seismic wave. So I'm showing you here is the anhydrous way, the VP and VS calculated based on this model. So the next step of this program is that we want to see how hydrogens and ions could change the elastic properties. So as I mentioned earlier, hydrogen can replace magnesiums or silicates to enter water ring structures. And based on that, you could imagine that Berg modulus can change. And yes, that is the case. So here I collect a database from previous studies, which show on the right-hand side, and I do a linear fit on the left-hand side. So you can see how the Berg modulus, shear modulus, also density decrease with water contents and increase with iron contents. So now, with all the experiments from previous studies, we will be able to see how those components change the physical elastic properties. And then we can use, so now we can use those information and go back to change the water contents, iron contents, and play with the data to see how it changed the overall velocities. So that's how we did next. So now we assume the whole man is not dry, it's saturated with water. And based on the relationship I just showed you, we will be able to calculate a new VP and VS, which showing you here is the blue line. So now you can see in the blue lines definitely lower than the red line, especially in the transition zone. That's because for the water and remonite, it can contain like 3% water, but for the ordinance, it can only contain like 0.3% water. So that's why for the ordinance, this decrease is less obvious than the water and remonite. So now I'm showing you how the Hyman's program can show how the water contents and iron contents play with the seismic velocity. So the next thing is that can we also see any other parameters can change the velocity? And that is yes. So when play with the parameters, we increase the iron contents, we lower the temperatures and increase the temperatures, adding water to see how each things fit with each other. So the conclusion for us is that for some amount of decrease in the shear wave velocity, so in this case, drop about 0.15 kilometers per second, you need to saturate with 50% of the water, which means that water contain like 1.63% of water and remonite contain like 1.5% of water. That's equal to increase the whole mantle by 160 degrees, also likely to increase the iron contents in the ordinance water remonite by 7%. So this is an equal place. So now probably notice how each parameter play a role in decreasing the seismic wave. The next thing is that how to apply those things to the earth science real problems. So to answer that, I also provide a case studies. So here we are looking at is the North American plates. So what I'm interested in is the East Coast of the United States. So which here showing you here the red line. So what's interesting here, if we look into the cross sections of this one and extract to see what it looks like, this is the tomography models from the previous studies. And here, this is, so let me explain a little bit about the seismic wave. So this actually showing you that how the seismic wave is deviated from the reference models. So the warmer the warmer color you see in the regions is the lower the seismic wave is, and the cooler the color is like green or even blue, which means the velocity is faster. So at the eastern coast, at the transition zone regions, here is the place that actually indicate that we have a low velocity zone. So the interesting question is what can cause this low velocity zone? From the previous slide, you know there's 3 parameters that can actually change those things, iron contents, water contents, and also temperatures. So how do we determine which one is the main contributions? So this is the beauty of the geology settings there, is that first, there's no heat source there, there's no mantle plumes, so it's not possible to get heat from the core. And the second one is that there's no radioactivity elements there, so it's not possible the elements will generate heat at those regions. And the last thing is that no evidence can show that the element from there is actually iron rich. So now from the geology observation, we already eliminated 2 parameters. It can't be temperature, it can't be iron contents. So eliminate all the other possibilities. The only one left is the water contents. And also there's geology setting that actually support the water, because that's previously there's a slab there, and slab could usually transport water from the surface to the deep earth, and then the hydrous minerals break out and release the water. So that can explain where we got the water. So the next thing for us to think is that could we quantify this? So to do this, we actually need to know how the velocity dropped. So to answer that, for the North American plate here, we show 2 seismic velocity profile. So the one is the black one, shown you here, is in the center of the United States, which there's no seismic anomaly. So we can extract the first dashed line here, and then we extract the velocity profile inside the anomaly. That's why the light green line showing you here. So we can extract the information from there, and we get this line. So now we can see can drop a little bit in the VS. So the next thing is that we want to know how much water contents can drop the mineralogy model by the same amount. So to do that, we generate 3 water profile. So showing you from the A panel, the red one is actually indicate there's no water at all. It's completely dry. And then there's the green one indicates like 20% water content, 20% water storage capacity, which indicate that for wasserite, it's about 0.6% of water. And for the remonite, that's about 0.5% of water. And then it's the blue one. We assume it's completely saturated with water. So we compare those 3 profiles, and it's interesting to find that so now we can generate a VS profile, and here is showing you the VS profile based on the water content we have. The red one is completely dry. The green one is containing about 20% of water, and then the blue one is completely saturated with water. And the interesting to find is that the 20% water contents can actually decrease the velocity. The amount is equal to the one we observe in the anomalies. So here the conclusion is that it's likely for the east coast of the United States, they can contain like 20% of water in Olivan, wasserite, and remonite. So this is how we use the high pressure data to explain the observation from seismology. And that's the research I did for the past few years in Northwestern. And in lots I want to acknowledge some of them, my supervisor, Steve, Suzanne, and Craig. Also want to thank the collaborators, and also want to thank the people in our departments, and last, I want to thank the funding from DOE, NSF, GSCAR, and Northwestern. And that's my presentations, and thank you.
Thank you, Faye, for a very nice talk. We have plenty of time for questions or comments. Just use the chat box or simply unmute yourself. Maybe I'll start by asking, I didn't see you listing, and perhaps I missed it, the actual composition of the Japanite.
Oh, yes. Let's see. Yes, that's my fault. I forgot to list it here.
Can you state roughly what it is? How much? The various elements?
Yes, so it's basically like garnet. So it's like MG. Let me see if I can get those size number out here. Yeah, it's like Mg2 Fe3Si3O12.
And you mentioned it replaces majorite.
Yes, it's likely to replace majorite in the base of the transition zone.
Okay. More questions or comments? Perhaps another one, a technical one. Can you say a little bit more about how you did the X-ray measurements going back to the very first work on Wadsleyite? I mean, you know, how good was the refinement and how extensive was the data set and so on?
Sorry, I didn't really follow. What's the question again?
Can you say a little bit more about the refinement of the X-ray data here for Wadsleyite? What kind of measurement was it? How many reflections? Something about the quality of the fits and so on.
Oh yes, so the quality fits quite well. So at the higher pressures, I think we can still obtain about 500 peaks. I think so. Not the unique peaks. I mean the actual observations. And the fit result for the R1 is also quite well. It's about like 9% about the resurgence. So the R1 is like 9.
Okay, there's another question about Japanite. Do you want to ask it, Paul?
Sure. Yeah. Do we know anything about the velocity anisotropy of Japanite?
I believe yes. That's anisotropy because that the two axes, the one is significantly more compressible than the other ones, but I cannot answer the precise number because we never measure the velocity. But we suspect that's
okay.
Yeah.
Oh, sorry. I just saying I was only asking because if the EOS parameters are very close to garnet, it might still be visible in anisotropy. Since garnet's quite isotropic. I don't know.
Yes, right. But we didn't measure the velocity, so we can't certain about that.
Okay, thank you.
Any more questions? Maybe I'll ask another one. Have any measurements of the infrared spectrum or the Raman spectrum of the particular samples you studied of Wadsleyite been carried out to help illuminate the role and the characterization of the hydrogen in this interesting site that's been the focus of so much attention?
Yes, that was been done by Steve's previous grad student. So she collected the infrared data and published on GGR 2015. So from that, yes, it's actually confirmed that the most size is still around 0104, the 0104 distance. And there's also probably another one, but mainly on the 0103 distance.
Has anything been done under pressure, under the same ranges of pressure that you studied by diffraction?
No, the high pressure infrared study is currently doing by Lydia Thompson, so we haven't got the data yet, but she's working on that.
Okay, thanks. Okay, another question. Go ahead and ask.
A very excellent talk. I just wonder for your hydrous Wadsleyite samples, is there possible other hydration mechanism like the copper substitution of ferric iron plus hydrogen to substitute the silicon?
Yes, that's a very good question. So it's possible. So I also did the Mooseball spectrum. So it seems like ferric ions could enter tetrahedral sites, but those cannot be the direct evidence to support the mechanisms. You can only just like hints it's possible. So that's, I mean, from my data, I can't directly prove that.
Yes. There is a paper, I think, in 2014 by Smith. They measured the FTIR of their Wozniak sample, and they show a peak at they show a different peak with the Wozniak sample, which is under the reduced condition. Yeah, I think it's an interesting paper.
Yes, yes, aware of that. Yes, right. That's true. So actually, I believe the paper you mentioned that's actually found a new peak is in the place ultra distance, if I remember correctly. Yes, right. That is correct. But also the peaks. So the first peak is weak, and second, if this mechanism will assist, the hydrogens can be that place. I mean, generally, there's a lot of places can be the hydrogens can locate it at, and that's definitely a possible place for oxygen hydrogens to locate. But from our X-ray diffraction. So first, X-ray diffraction is not good to directly observe hydrogens. So all the information we can get is actually from the compressibilities. And because the ultra, even though it can contain hydrogens there, it's likely that's not enough for us to observe a change the compressibility of the OO distance. So yeah, I mean, I know this is very likely possible that this mechanism happens, but from our from equilibrium state and compressibility studies, we don't have enough quality data to support that.
Okay, thank you for your answer.
Okay, any more questions? Okay, another one. Go ahead and ask. Nada, if you'd like.
Yeah, okay. First, thank you for the interesting talk. And my question is, how did you quantify the H2O content of the Wozniak?
Oh, yes, it's doing that in two ways. So first is from FTIR spectrums, and the second one is from SIMS measurements. So for in our studies, because for the very high-risk one, we believe SIMS could provide a much precise data. So we use SIMS to quantify the water contents in the crystal.
And which standard did you use then for the SIMS?
Oh, actually, that one forgot. That I didn't perform the experiment, so I need to double check on that. I'm sorry.
Oh, okay. Thank you very much. Thank you. Nice talk. Thank you.
Okay.
Okay, any more questions? If not, thank you very much, Faye, and good luck with your thesis. And thank you all for joining us.